The last talk of the conference. I cannot tell you how many times I've drawn this slot in a conference, but thank you all for staying till the end. So this work was done as a part of the undergraduate thesis of Preeti Arunapuram. Since she graduated, she's now in the real world, and so she couldn't make it to the conference, so I get to present it. She worked with Jacob Bartel, who's my PhD student, and she did most of her work independently. Most of the slides are hers, and I was 2 levels removed from her, so I'll try to my best to interpret what she did. Actually, the previous talk has already made the setting, and maybe you can answer questions that I can't, because you know the data better than I do. Oh, sorry. I'm going to really kill your paper, really say bad things about your paper while you're going. So let me question, since there's been so much work in so much emphasis on access control in this conference, let me pose this the problem as an access control problem. Okay, so supposing you have to go and send an email message to a bunch of people like the following, and you're trying to find a slot for someone to meet. Anybody who's tried to organize a talk knows this problem. There are two things you have to know. Okay. There's 2 kinds of help a system can provide. First, it can help you choose, specify the names in the email automatically. Okay, so Andrew's work said that, look, I'll predict a group, and you just name a group rather than specify each individual. Okay, so given that you have to share information with some people, and given that you know who you should share the information with, certain kinds of work can ease that effort. The other thing is that the system could also help you figure out who should send the information. Okay, supposing you don't quite know who you should send it to, there are alternative sets of people you can send it to. You might want help from the system. Okay, so this talk addresses that question. Okay, in a very broad way. Why might you want to know that? So what kind of information might you want from the system to help answer that question? Then we'll see why you might want to know that. Are these the appropriate recipients? Are they the experts? Are they the people who will answer the question? Will you get the answer you need? If you're trying to schedule a talk and everybody says, no, I won't host the speaker, your message was sent for no good reason. Okay? And you might get an answer, but too late. Okay? So the talk is next week and you get the answer in a month. Okay? So this is the kind of information the system can help you with. And we are going to just look at response time, okay, like the previous talk. And now we can try to get into why such a prediction would be useful. So what's the cost of making the wrong choice? In access control, there's a need-to-know principle that don't disclose information to people who don't need to know about it. If you sent a message to somebody who's not responding, or that message was useless, you unnecessarily disclose some information. Okay? And on the flip side, that person is not interested in that information, so you unnecessarily spammed him. You essentially wrote to his or her space. Okay? So good prediction can reduce this access control cost by allowing a better choice of recipients. Okay? That's one reason to know response times. That has to do with access control. Even when you know exactly who you should send the information to, or there's only one person you can send the information to, it might be helpful to know when the response will come. You don't unnecessarily get frustrated or worried when the response doesn't come. As in the previous talk, you may want to modify what you send to get an earlier response. Okay? You may use a more alternative mechanism. So if you know by email you won't get the answer quickly, you might IM them or you might call them. Okay? If you know you're going to get a response to some question in a week, then you might delay your project to start after that week rather than before, so you can schedule your activities appropriately. Okay? And who knows what other reasons there are. If you have any ideas, please let us know, because this may be a solution looking for a problem. Okay? When I tell people we're doing this work, they say, oh, so neat. And I said, so why would you use it? And then they start scratching their head. Okay, so please scratch your heads and let me know if there are other reasons why you might want to know when a message gets its response time. Okay. Information is shared in many domains. Some are synchronous, some are asynchronous. And, we are not trying to answer the question for all domains. And we just chose one particular domain, which is basically Stack Overflow, which is part of Stack Exchange. Okay. So the idea is, which was suggested by one of the questions in the previous session, that as you're composing your post, you get a response. And as we saw in the previous talk, there is time to the first answer and time to the accepted answer. So you get a response saying you will get the first answer within so much time and the accepted answer within so much time. Okay? So that's what we'd like to build. This is a fake pop-up. Okay? We don't really have a working system, but that's the goal we are going towards. Okay? And no previous work has this exact goal. There on response time, maybe the previous talk was one of that piece of was one such work, and this work has spanned all kinds of domains. Let me actually put the pointer on here. Okay, so there's work in IM, email, social networks, forums. In fact, there was a question that was asked that how does that work in the previous paper relate to other domains? And there are people in other domains who've looked at features that are relevant. Okay, and there's some people have tried to predict whether you will get an answer back. Some have tried to predict, have addressed the speed issue, and so they've identified features influencing liveness and speed. And some people have just left it at correlation, which is what the previous talk did. And some people, at least one group has tried to go beyond that, or two groups. One group has tried to predict response times, and another group has tried to predict liveness. Okay, so there's no Stack Overflow here, so we are in a brand new territory, and that has good things and bad things about it. When you're in a brand new territory, you don't know how to think about the problem. When you're in brand new territory, the bar is very low. Okay, you just have to do better stupid approaches, okay, or the baseline approaches. So what you could do is just take the average accepted time and predict that to be your accepted time, okay? Or the average earliest times, you could take the averages of the two times, or you could take the medians, okay? And if you look at this is data collected over, I think, 2 million messages. The medians are smaller than the means, which indicates that the distribution is skewed. Actually see that here, that there's a long tail, and as we saw in the previous talk, some messages never get answers, but the median is pretty small. Okay, but this is not a very intelligent approach. Like I said, it's a stupid approach. Are there better ones that are less stupid than this? Okay, not necessarily very intelligent, and that was the question we were trying to answer here. Okay, and this approach is featureless. It just looks at the average times. So you can imagine featureless approaches, and you can imagine approaches with features. Okay, and if you're doing with features, you've got to figure out what features. Okay, distributions they vary depending on the tag used in the post. Okay, so you can see very large variation. Okay, and in fact, I think this is consistent with what we heard in the previous talk. More specific is better. So you see here that the question about Visual Studio takes a very long time to answer, whereas the question about 2008 or 2010 Visual Studio gets a much quicker answer. Okay. So if you're just trying to improve response times, you might want to be more specific, which I think is consistent with what we heard in the previous talk. Okay. So tags is going to be one of the features we look at. Stack Overflow specific, we can also find features that are more general from the work that has been in other domains. So that was our next task, that to look at some of these features in other domains, see if they're applicable, and how applicable do they seem to be. Okay? And so these are some of the features that people have found to correlate with response times. And the question was, do these apply to Stack Overflow? Length of post. Okay? That in the social networking domain, people have found that it correlates with response time. When we're talking about Stack Overflow in code, it's not clear whether length, how should you divide the message? By words, by characters, by procedures? And in fact, I think we heard in the previous talk that the length of the message doesn't make any difference, at least in the two forums that were examined in that talk. okay? So we didn't even go this route, okay? And I think the previous talk sort of validates why we shouldn't, why that was a good idea, okay? But what we did do was look at the length of the title, okay? And that makes intuitive sense, right? Because if you're going to, that's the first thing you see, and you might make your decision at that point. And intuitively, okay, so that's what we did, and we did title length in terms of, and we found that you can't just take title length and put it in the equation and get the exact time when you get the response. Okay, there's a whole scatter plot, and for each title length, the time varies. Okay, so but what we did do was we see that the means of the plots you get, distributions you get for each title length, have a systematic relationship with the title length. In fact, it's a quadratic relationship, and that makes intuitive sense. If you have no title, if it's 0 words, then the person doesn't know what you're talking about. If you have infinite number of words, they don't know what you're talking about. So there is some optimal value in between. So that seemed to indicate that it's a feature we should worth investigating. Okay. People have found that the kind of pronouns you use in other domains and punctuation you use correlates with response time. These are some figures showing PCA analysis that Preeti did, and from that analysis we couldn't find any correlation, at least in this domain. Okay. People were talking about time of day and day of week. Again, people have found in IM, a group at CMU, that both of these values correlate. In the previous talk with the Microsoft forum, they found it correlated, but we didn't find any correlation between time of day and day of week. And I think the reason why we didn't find it, and the CMU guys found it, is that that was one-to-one communication. This is one-to-N, where the N people are globally distributed. So what does time of day mean? Okay. And so that's what we found. Okay. So basically, we used two features, investigated two features, title length and tags. We investigated many features, but we used two features in our prediction. So now we have to go and use these features and not use features to come up with a bunch of approaches that could perhaps do better than the baseline approaches. Okay. Now, by the way, predicting time is a very hard problem. If I was to ask you, and I was to give you a specific message from me, and ask you when will you respond, okay, after the conference, you won't be able to give a precise time. Okay? If you can't do that, I suspect you won't be able to give the precise time. And if you can't do that, how can a system give you a precise time? Okay? So, but you might be able to say that, look, I'll do it within a week, or I'll do it, within 2 days. So you want to provide an approximate answer rather than an exact answer. Okay? So you want to divide the time into ranges and predict a time range rather than a specific time. Okay? And what you could do is have constant time ranges, okay? 2.4 seconds, for instance. Okay? And if you do that, how many time ranges will you have? You'll have a lot of them. I mean, some of these answers come in years. Okay? And time range differences are absolute. If you predict 10 seconds and the actual time was 20 seconds, you're just, you're just 50% off. But if the actual answer was 10 years and you were off by 10 seconds, that's not bad, right? So constant time ranges, so maybe we want variable time ranges, okay? If you're going to have variable time ranges, then you have even more difficult problem. What is the width of each time range and how many time ranges do you have? Okay? And you could use some intuitive things. You could so then you could use so you define the time ranges, and you can do this statically or dynamically. Okay? Statically means that you just fix some times. Okay? You can say seconds, minutes, hours, days, weeks, years. In fact, that was my suggestion. Okay? And Jacob, who was the one who was working with Preeti, he didn't like that idea. He said, that's arbitrary. it doesn't mean that that's useful to the people. So we will have to do some user studies to figure out whether these are meaningful ranges or not. So maybe we won't do user studies and see whether the data are clustered in such a way that you can come up with time ranges corresponding to each cluster. So you cluster the data, and then with each cluster defines a time range. Okay, so that's what we did. We used k-means, and quite arbitrarily we identified 25 time ranges. And these are the ranges. These are some of the ranges. The paper gives all the ranges. And they do have a nice property that as you go further, the size of the time range is proportional to its lower or higher limit, okay, which is what we wanted. So that's good. So now that we have the time ranges, how do we predict the time range? Okay. A more intelligent approach than the previous before. We can predict the average time range or the median time range. Okay. Or now that we've gone from a continuous time variable to a discrete set of time variables, we can look at the mode of the variable and predict the most frequent time range. Okay. So that gives you another alternative that we tried. The problem with these mean, medium, and most frequent is that for every question we get the same answer. Right? It may be fine, but it just seems wrong. The answer should depend on what you put in. So we can try the roulette wheel algorithm, which draws probabilistically from the distribution of times. Okay? So the idea is that the heads is 60% likely and tails is 40% likely, then 60% of the time we predict heads and 40% of the time we predict tails. Okay? So Preeti tried that particular algorithm also. Okay, and basically it's not head and tails, it's many ranges. We can look at the probability of each range based on how many questions get answered in that time range, and probabilistically draw from this information. Okay, so now we have our featureless approaches, and the next question is how can we go and create a featured approaches to compare with. And we have two features, title and length and tags. And as the paper says, we're looking at distributions in all of our work. So what we do is, so what happened in this work was that we used one feature independent distribution to give all our answers. Okay. Now what we'll do is we'll use one or more feature specific distributions to give our answers. That's how we're going to go to the featured approach. So for title length, for each message has exactly one title length. So there's only one distribution for that title length. So what we can do is predict the mean, median for that in that distribution, most frequent in that distribution, or we can use a roulette wheel in that distribution. Okay. So this is now one distribution, but it's feature specific. In terms of tags, a message can be sent to multiple tags. So now we have a harder problem. We've got to use n distributions to construct our answer. Okay? And how do you combine the distributions? Again, to draw probabilistic, to use probability here. In the roulette wheel approach, we used one distribution and we looked at the frequency of it in each time range, and that was used as a weight. Now what we'll do is apply weights to answers from multiple distributions. Okay. So what does it mean? Let's look at an example. Let's say you have two tags, and one of the tags predicts that the first time range is the right one, and 40% of the answers come in that particular time range. Or there's 40% chance that that time range is correct. And the other one predicts the fourth time range, and there's a 20% chance in this other distribution that this answer is correct. Okay? So we give more weight, double the weight to the first one compared to the second one. Okay? So when you're giving weights, there's an issue. What do you take the weighted average of? The lower limit, the mean, or the upper limit? Which raises an even bigger question. When you go and take two different distributions, and you take two different time ranges from two different distributions with different widths, what is the width of the predicted distribution? Okay? And Preeti had a pretty elegant answer to this, that she was not weighing, she was not taking the weights of the limits, but the weights of the indexes. Okay? So if this is index 1 and this is index 4 here, then she was going to predict index 2 for this particular weights. Okay? And the nice property here is, so that's the prediction, that we will not predict an artificial time range. We will predict one of the time ranges that we have found based on our clustering. Okay? So we have now a bunch of featureless approaches. We have a bunch of tag-based approaches. A bunch of, title-based and tag-based. I think I just copied the slide over. But we basically have title-based, tag-based, and featureless. How do they compare? Okay? And so what metric should we use? Well, we could look at the actual time minus predicted time. Okay? So that's the absolute error. And for the reasons I described earlier, this is not the right metric, because the 10-minute error is more severe when the prediction time is low than when the actual time is low rather than when the actual time is high. Okay? Okay, we can take actual time minus predicted time and divide by actual time. And so we get a scale, we can get an idea of the scale of when we'll get the response. Okay? And here we can tolerate large amounts of errors. So we can even, for instance, tolerate a 600% error. Okay, so supposing the answer came in 1 day, and I told you the answer will come in 6 days. Okay, at least you know that the answer will come in days rather than in weeks. Okay, because 7 days makes a week. So this is not a this kind of error is what we can tolerate when we're just focusing on scale. Okay. However, this formula is not very useful. Because if I always predicted 0, then the scale error will be exactly 1. Okay, so clearly there's something wrong here. Okay, now by the predicted time rather than the actual time, and then you have the flip problem. If I always predict infinity, then then again I will get a scale error of less than or equal to 1. Okay, is take the min of predicted time and actual time to give you a better idea of the cost of that error. Okay, but then you get into a problem that the actual time is a single scalar. Okay, it's 10 minutes, 5 days, 10 years, and we are predicting a range. So which value should we take? When we compare for predicted time, what value should we take? The lower limit, the higher limit, or some value in between? And what Preeti did was she just took the value that was closer to the actual time. Okay, and that may not have been a very fair metric. Maybe we should have taken the median, but that would give us the best results. Okay, so when you look at our results, please consider this approximation. How did these approaches compare? And what conclusions can we draw from our data? Well, features helped. Okay, so the bottom half of the approaches have features, and you can see that the error in accepted answers and earliest answers is much smaller. Okay, so even if these are not good prediction features for prediction, at least they do indicate correlation. Okay, also, so features help. Okay. The maximally occurring time range was the best in the featureless approach and in the featured approach. Okay? And the intuition for that is that a large number of messages occurred in the most frequent range. Okay? So that makes sense. When you look at earliest answers, though, the tags helped far more than title length. Okay? That's what we found. My theory is that with the accepted answers, maybe like it was said in the earlier talk, a small group of Microsoft people or some experts answer that question, and maybe their behavior is more regular than the whole world, which can always provide an answer, not necessarily the accepted answer. Okay, that's my theory. But it's intuitively good that tags which have more semantic content are more useful than title lengths, which are more syntactic in nature. Okay, and if you look at the answers, these are very strong results. That, I said 600% error should be fine if you're trying to distinguish between a week and a day. And we are getting errors of 0.4 in the accepted answers and earliest answers 1.3. Okay, and maybe we should look at the distribution of these errors. And the distribution, again, we see that there is a very small number of messages relatively that have an error of around 1, because it was 1.4, which we approximate to 1. So we were basically considering an error between 0 and 1 if we look at this, integer values. And actually, no, we are considering decimal values too, but for some reason she didn't plot values more than 1. But a large number of answers were correct with 0 error, and there were a few with error of 1.0. Okay, the maximum and the average error was 1.4, as we saw. Okay, this might be again a copy and paste problem. Okay, so but basically the both distributions showed that there were a lot of questions answered in the correctly. Okay, so future work. We looked at just 100 tags. There are many more tags, and we couldn't deal with so many tags. So just as we use clustering for time ranges, it might be useful to use clustering for tags also and divide tags into equivalence classes so that we can deal with a larger number of tags. Okay. Going back to the domains we investigated, in the we've seen that in synchronous domain, people have addressed instant messaging, where they used where that work basically divided it into statically defined time ranges. Okay, and in asynchronous, we actually did try email, news, and Stack Overflow, all 3 domains. Our results were not very good for email and news. Okay, so Stack Overflow was a much easier problem to deal with, and future work should address the other domains too, and then you will require far more complicated and sophisticated approaches, I think, than what we have right now. Okay, so in conclusion, based on our findings, time of day, punctuation, keywords had little association to response times. Okay, analysis on the number of sentences, which was the length of the post that people have looked at earlier, does not apply in Stack Overflow. We don't talk in sentences. Some reviewers suggested that we can look at the number of procedures, a number of, some programming units there. Title lengths showed a quadratic relationship. The dynamic time range approach using predicting time ranges worked better than just predicting absolute times. And the most frequent time range was the best among both the featureless and the featured approaches. And for the earliest answer, most frequent with tags gave you the best results. Okay, and predicting the time to the earliest answer was more difficult than predicting the time to the accepted answer. Okay, that's my talk.
Okay.